All right. We'll actually derive the Gibbs Helmholtz equation, okay, or Helmholtz equations. So that's physical chemistry. We'll look at how to derive. It's actually a very big derivation. That's why most is always accredited with 10 marks. So it deserves it. So let us see how it is complicated and we'll simplify it. So you just have to master the steps, okay? So we start. So we know Gibbs free energy is given as follow. So Gibbs free energy is given as Gibbs, all right. Gibbs free energy is given as, okay. Gibbs free energy is given as Gibbs is equal to enthalpy, okay, plus, no, this minus, just upon starting, okay, minus T S. So this condition is actually at constant temperature. So that means at constant temperature, what will be changing are this one, and Gibbs. So we can have it can be a state function by saying we have initial and the final. Okay. So this is the state function. Okay. So what you do is then you say, okay, um, initial function will be G1 is equal to enthalpy 1, okay, minus T at constant temperature, then enthalpy, I mean entropy, S is entropy by the way, 1. So again, we can have G at different temperature, can you still obtain the same enthalpy 2 minus temperature, the same constant temperature, then enthalpy, I mean entropy 2. So from there, this will call it equation 1, then this one equation 2. So you can be numbering by the way. So we say now 2 minus 1, okay. When you subtract that, there will be change in Gibbs, okay. Then also there is change in enthalpy, okay. I don't have to write that because it's the subtraction itself tells you the change, so I don't have to write that. Then minus what was changed, temperature is constant, what was changing in the enthalpy. So this is the equation 3. So please master this. We'll come back to this. Master it. I said master it. Okay. So this is equation 3. Okay. So now we go to equation 4. Equation 4. Okay. So we are done here. So what we are going to do is we are going to actually substitute in the following. We know that so from equation 3, okay, so that is equation 3. Then again, what we are going to say, we know that um, it was given as Gibbs is equal to, okay, Gibbs is equal to um, H minus T delta S, okay. No, we don't. It was just given. This is the initial equation that I gave. So again, we go back to it, okay. So from there, we know now enthalpy, okay. Enthalpy H is given from the first law of thermodynamic. It says it's equals to internal energy plus work, which is PV, okay. PdV, that's all, just PV. This is the given equation. So then, and the other thing that we know is that um, we know that is it. Then we'll substitute in the equation. So we're going to substitute in this equation, okay. So we substitute, so that was equation, okay. So this is 3, we end there. So I'll make 4 then. I'll say G is equals to wherever there's enthalpy, I'll put this. So say change in internal energy, or just internal energy plus P V, okay. So from there then minus T S. Okay, you remember it was from here. I mean from here. I've just substituted the H. Then from there, I'm going to now differentiate complete derivation, which is actually, which will give us dg is equals to du. Okay, change in u plus, this is now differentiation by a product rule. So we'll actually say we maintain P, then dV again, plus we maintain V, then you say dP. Then minus, also this is also a product rule. So say I'll maintain T, then ds. Again, I'll maintain S, then dt. That's how we differentiate product rule. Then from there, we know that, okay, we know that um, from actually enthalpy of formation, I mean heat of enthalpy or entropy. So we know that um, change in S or just ds is given as the heat given over the temperature. So that's how we get the entropy. Okay. So from there again, we know that from first law, we know that um, du, okay, is equal to um, is equals to q minus um, p dv, which is work. Okay, so that will be q is equals to du plus p dv. That's all. So we are saying, what you are trying to say is, so what I'm trying to say is, from first law, so meaning that q is equals to du then plus p dv. So this is from first law. So I'll substitute. I can see this du and the p dv is there. Okay, so these ones, they'll give me a certain value. Then also this one here, this q that you're able to see there, it is this times that, so it will be q. Okay, if I multiply, make q the subject of the formula there, it will be t ds. You have seen, because I will multiply like that, then the t will multiply there. So that's what. So I have now to this one and also these two equations, of which I need to substitute. There is t ds there. I can see t ds is there. So I'll substitute there. So we have dg is equals to, here we are substituting now. Here we are substituting now. We are putting what? Q there. Okay, so say Q, okay, plus V dP, okay, minus there, what are we substituting? We are substituting Q. Okay, so that will be Q again, then minus S dt, like that. Then we say dg is equals to this, and this goes right. So say V dP S dt. Okay, this you will even find it at, so let me just give it equation 5 or equation 4. Okay, okay, then this you find it under Maxwell equation relations, you find it. So from here, since this was the differentiation, okay, so at constant, so I'll call it at constant um, pressure, at constant pressure, differentiating this one at constant pressure with respect to T, that will be dt dg over dt. Okay, at what constant pressure is equals to, at constant pressure, meaning dp is equals to 0, this will be cancelled definitely, so that will be 0. So also remain with s, then dt. Okay, dt, then again dt, differentiating everything by dt, so that will cancel, right? So that will be just dg, okay, over dt at constant pressure is equals to negative s. So sometimes they'll bring at, you end at this point, you get, they will say show that this, so you need to know where it is coming from. Sometimes they can use internal and free energy there, but here it's Gibbs energy. Okay, so from there we continue. So this will be numbered as equation 5. Okay, this will be numbered as equation 5. So now pay attention. Equation 5 we have there. So from there, then what we are going to do is okay, G as well is a state function, so it can vary as well as in the form of the following. Okay, so we can have dg, okay, initial dg over dt, okay. So it's a state function g, so I can say g1 is equal to, again, it will produce different entropy, so 1 like that, then at constant again I can have, so this I'll name it 6, equation 6. Then again I can have dg 2, okay, then at dt at constant pressure is equals to negative s2, okay. This will be equation 7. All right, so from there then I will differentiate the two, so there will be a change in the Gibbs only, and also the change in the what, in the entropy. Okay, so entropy and Gibbs, there will be a change. So here, if Gibbs is to change, so it will be d change in Gibbs free, okay, over dt. All right. All right, so then this is done at constant pressure, then is equals to, there's also change in what, there's also change in what, in entropy. So there's a change in entropy, because the entropy 2 minus entropy 1, there will be just a change in that. We leave it like that. You have seen? So from there, from that equation 3 that we gave at first, remember equation 3? We gave equation 3, it was change in d, it gives to say um, change in g, okay, we got change in entropy, then minus t change in s. So you have seen now that we'll substitute now where there's s, okay. In fact, yes, we'll substitute where there's s there. In fact, this negative I can take it there, okay. So we are just substituting now, so it will be change in Gibbs is equals to entropy change minus t, okay. There's minus again, I'm now substituting, okay. I'm now substituting because entropy change is equals to that, and there's a negative, so I'll attach a negative there, okay. So that will be d change in g over, okay, dt at constant pressure, okay. So that means that the negative and the negative will multiply, so that will be, okay, so the negative, so we'll say we have now the change in Gibbs free energy is equals to entropy change. This will be now plus, because this and this it will be plus temperature. Then, okay, temperature, open bracket, we have now d change in Gibbs over change in temperature at constant pressure. So this is the famous equation you have been seeing. This is Gibbs Helmholtz equation. So that's how we derive it. Thank you very much. Otherwise, keep practicing. It's a very simple one. Just repeat it, and you get it. Otherwise, I understand physical chemistry is not something to play with, because you have to practice for you to master these numbers, dg's, the something, the what. So it was so sweet, such that we made the third equation, of which we used at the end, and the other equation was made from differentiating complete derivative, okay. So this was so sweet, then we had to use it later, okay. So that is it. So you number it according to your lecturer, so derive the way your lecturer wants, but otherwise this is the whole concept, the way you can do it. Thank you very much.